Hey guys, this is Ajmera. In today's video, we'll be covering basic chemistry. This is not necessarily chemistry that you would need to know for a chemistry class, but rather the chemistry that is required for you to know for AP Biology. In this first part of the video, we will be talking about protons, electrons, and neutrons. Protons, electrons, and neutrons are considered subatomic particles, meaning that they are particles that exist inside of an atom. So let's draw an atom out. This is my wonderful drawing of an atom, in which in the center is our nucleus. The nucleus consists of protons, which are positively charged, and neutrons, which have no charge. In these rings, at least they're represented like rings in diagrams. In real life, they just exist in clouds, are electrons. These electrons move very fast. This diagram is not to scale. The electrons would realistically be much farther away from the nucleus. But anyway, these electrons all have negative charges and exist in what we call electron clouds. So how is one atom different from another atom? Like how is a hydrogen atom different from, let's say, a helium atom? Well, all atoms are different based on the number of protons that they have. For example, let's look at hydrogen. In the periodic table, hydrogen is number 1 in the periodic table. Yeah, let's make it a little bit. That means that it has 1 proton. That also means, however, that it has 1 electron. And since the mass in hydrogen is labeled as approximately 1, that means that it'll have 0 neutrons. Why is this? Why is the mass 1, not 2? Because there's a proton and electron. That's because most of the mass of an atom is determined by its protons and neutrons. The electron's mass is so minute such that it cannot even be considered in the atomic mass. So if the atomic mass is 1 and the atom is atomic number 1, meaning that it has 1 proton, that means that it'll have 0 neutrons because the sum of the protons plus the neutrons equals the atomic mass. So we can get all that data just by knowing that hydrogen is number 1 on the periodic table. And even if, let's say, for example, I donate an electron to hydrogen, and now it had 2 electrons, it would still be atomic. It would still be hydrogen. It would still be in atomic number 1. However, if I change the number of protons to, let's say, 2, then it would be helium. So I would have to change this, and I would have to change this, and then I would probably have to change that, then I would have to change that. So it differs just based on the number of protons. So what truly defines an atom is the number of protons it has. So how would we write out if an atom is missing an electron? Let's say, for example, a hydrogen is missing an electron. Let's think about this logically. If a hydrogen has a proton, it has no neutrons, and an electron, and if I were to remove that electron, then it would be overall positively charged. So then if you remove an electron from a hydrogen atom, it would be H+. This applies to any atom when you remove an electron. When you add an electron, however, let's look at that same situation again. You have a positive proton and you have a negative electron. If we were to add another negative electron, it will be overall negatively charged, thus calling it H-, because there's more electrons than protons, making it overall negatively charged. You might have heard the term radioactive isotope being thrown around in your chemistry or previous science classes. Now, what exactly does that mean? An isotope is an atom in which the number of neutrons is not equal to the number of protons, or it's not in its typical state of number of neutrons. So let's look at carbon 12. Okay, carbon 12 is the normal state for carbon. Carbon is atomic number 6. Let's just write that down here. So carbon 12. Okay, so that means it has 6. The 12 refers to its mass. So 6 protons, 6 E minus or electrons, just kind of shortens it up, and 6 neutrons. This is the typical state for carbon. If it were to have any more neutrons, again, it would still be carbon because of the number of protons being consistent, but now it would be an isotope of carbon. This would mean that if there were enough neutrons in certain atoms, they would undergo radioactive decay to reduce the atoms back to, or to reduce the number of neutrons back to a state of equilibrium. Now, for isotopes, there is a notation for which you do write them. For isotope notation, you write the element. So let's take hydrogen, for example. You write its mass over here, and you write the number of protons, or its atomic number, here. Let's say we were looking at hydrogen 3. So it would have a mass of 3. Let's rewrite that. Have a mass of 3, and we know that the atomic number of hydrogen is 1. So this would be the notation for it. Now let's move on to the octet rule and bonding. If you're still new to some of the chemistry concepts I will be talking about in this video, you might want to pull out a periodic table. The octet rule basically states that an atom needs 8 electrons in its outermost shell to be considered complete, or it can't bond with any other atoms, unless there's a high amount of energy put into it. So if you look at the periodic table, you know that all the noble gases, the column all the way to the right, the noble gases are already satisfying the octet rule because the noble gases are known to not be able to bond with any other substance because their outermost shell is completely filled. Even though the octet rule does imply 8, 8 does not apply to all atoms. For example, hydrogen and helium, they only have 2 because their outermost shell is the first shell. However, the octet rule continues to apply until about the 4th or 5th rows of the periodic table, in which the number starts to increase. But biology does not necessarily always concern those atoms. So to demonstrate how this rule works, let's look at carbon. Okay, carbon is atomic number 6. Let's write that down. Carbon is atomic number 6, right? So if carbon is atomic number 6, what does that mean? That means that it has 6 protons and 6 electrons. The number of neutrons is irrelevant for this. Since it has 6 electrons, if we draw out the number of shells, let's just write C first shell and the second shell. The first shell will have 2 of its electrons, and since we know that carbon has a total of 6 electrons, it means that there are 4 in its second shell. According to the octet rule, it would need 4 more because 4 plus 4 is 8. So that means that carbon can afford to bond in many different ways, including to itself easily. For example, CH4, each hydrogen has an electron, so that means that you can have, if you have 4 times the number of electrons, which is 1 in hydrogen, that would equal 4 electrons, which is just enough to satisfy the octet rule for carbon, which allows for CH4 or methane to occur. Now, the type of bond that I just mentioned is a covalent bond, without really even naming it. How can we tell if a bond between 2 atoms is covalent? Well, you can think of covalent as mutual. The electrons between atoms are being shared. So let's use the example of methane gas again. So we have carbon here, and now we're just going to draw out the outermost shell for this. So carbon, so it has 4 in its outermost shell, and then hydrogens each have 1 in their outermost shell. So So now all the hydrogens are satisfied and all the carbons are satisfied. They're, the thing about covalent bonds is that they're all reaching towards a common goal. They're both trying to fill up to their highest electron shell. Ionic bonds, on the other hand, work differently. So to demonstrate ionic bonds, let's just look at any atom let's just look at its outer shell. It has one extra electron, okay? And then if we look at another electron shell, it has 7. Now assuming that this has another shell within it, let's just say it has 2, okay? And this has 7, then these two substances would ionically bond. How would we know that? That's because this, the one that I just circled, sorry, the circling could kind of look like another electron shell, but this atom is willing to donate an electron to satisfy its octet rule because then it would then its outermost shell, which is its first shell, would be complete, and then donating that electron to this atom would satisfy this atom's octet rule because it would have 8 electrons in its outermost electron shell. Unlike covalent bonding, these two atoms do not have the same quote-unquote goal. The atom on the left, its goal is to go down in number of electrons, and the one on the right is trying to go up towards its highest complete shell. This would actually cause a charge. So the atom that loses an electron would overall be positively charged, and the one that gains an electron is considered to be negatively charged. These would cause each of them to be considered ions, which is why it's called ionic bonding. In biochemistry and organic chemistry, you will often hear the terms oxidation and reduction reactions, or redox reactions, which kind of encompasses the two of them. So oxidation is when the overall charge of an atom becomes more positive. So oxidation, let's just say if positive is up and negative is down, it's when the charge goes up. Reduction does not mean reduction of electrons, it actually means reduction of charge if we think about it like electron is down, proton is up. So reduction means down in charge, so that means it's more negative. Oxidation means it's more positive. So something's more negative, that means that it gained an electron. And if it's more positive, then it lost an electron to another atom. So almost all reactions, especially ones that occur in cells, such as photosynthesis and cellular respiration, have a lot of oxidation and reduction going on. For example, when we talk later about the electron transport chain, that's a really great example of how oxygen takes in electrons and it gets reduced, but it acts as an oxidizer. And that's why it's called oxidation actually, because oxygen is a really strong electron acceptor. So a lot of atoms lose electrons to oxygen. Now let's move on to electronegativity and polarity. Electronegativity, in simplest terms, is how much an atom wants to take electrons. The highest on the periodic table is fluorine. So, and the trend on the periodic table goes like this. When we go up to down in the periodic table, electronegativity goes up as we go up the periodic table. And when we go from left to right, it also goes up. So let's just say that hydrogen's here and helium is here. However, this does not mean that helium necessarily has the highest electronegativity. Fluorine has the highest electronegativity due to electron shielding and other properties of the atom that we won't necessarily be talking about in this video. When two atoms bond, their difference in electronegativity is largely what allows us to classify them as being just covalent, polar covalent, or ionic. The scale that we use for electronegativity difference is this. If the difference between two atoms, if the electronegativity difference between two atoms is from 0 to 0.2, we consider that nonpolar covalent. If it's from zero point 0.3 to 1.4, we consider it polar covalent. And if the electronegativity difference is greater than 1.5, at that point it's almost an atom giving away an electron to the other atom, so we would consider it to be ionic. But what do all these numbers mean in the context of biology? Let's look at water as an example. Water, with the formula of H2O, has, here let me leave some more room, has one oxygen and two hydrogens, right? So one oxygen, so let's look at the outermost shell for this one. An oxygen has, and it needs two more electrons, which it can get from the two hydrogens. So oxygen, then we have hydrogen. Also know that this is a covalent bond rather than an ionic bond because the electrons are being shared between the hydrogen and the oxygen. But what makes it polar? If we just look at the numbers, the electronegativity of oxygen is about 3.4. And the electronegativity of hydrogen is 2.2. So 3.4 minus 2.2 equals 1.2. If we look back at our scale, that would follow polar covalent. But if we were to not look at the electronegativity difference and rather just the electronegativity relative to other elements in the periodic table, oxygen has a pretty high electronegativity. That means that it's pulling, or it wants electrons more than the hydrogen atoms do. In the case of water, this means that the oxygen will be pulling on these electrons, on the hydrogen's electrons, so to speak, more than the hydrogens will. This would mean that the oxygen is overall negative, and since it's polar, we write it like this. So the oxygen is slightly negative, and because the hydrogens are sort of losing their electrons, they're not necessarily losing it completely like an ionic bond, but they're kind of partially giving the charge away to the oxygen. We would consider them partially positive on all ends. But how would this make a difference? How would being polar, or how would having charges make the properties of water be different than, let's say, methane? If we were to draw out the H2O molecule with just its charges rather than showing the electrons, the oxygen would be partially negative. I'm not going to write the partial symbol because that takes up too much space. And the hydrogens would be partially positive. This means that if I have multiple water molecules together, the oxygen of another water molecule would be attracted to the hydrogen of the other molecule. And these partial charges are these poles, which is why it's called polar. These poles allow water molecules to kind of stick together. These sort of bonds between intermolecular bonds, these are called hydrogen bonds. Hydrogen bonds are what allow adhesion and cohesion to occur between water and other polar molecules. Cohesion is when water sticks to itself. This is what allows capillary action to occur, which is the action of water moving up against gravity in plants, and it allows for adhesion, which is the sticking of water molecules to other polar molecules. In addition, these polar properties of water is what allows salt and sugar to dissolve in it. If we were to look at salt, NaCl, and if we were to just draw it out, one atom would be giving an electron to the other atom. This would mean that this is ionic. Ionic still means that it has a charge though. So an H2O is polar. So now these both have charges. These both have positive and negative charges. Much like the situation that I drew before with water molecules getting attracted to other water molecules, it would work in the same case, except the water would dissolve the salt. Essentially, if we were to draw this out, the water molecules would end up surrounding the sodium and chloride ions, causing what we call hydration shells. So the H2O, these would all be attracted to the negative chlorine ion, Cl minus. And then these ones would be attracted to the Na plus ion. Another property of water is its high heat of vaporization, meaning that it takes a lot of energy to turn water into water vapor, and to turn water in its liquid form into water in a gas form. This is because of these hydrogen bonds. These hydrogen bonds allow the molecules to cohere to each other while they're being heated and still stay in their liquid state. Another important property of water is high specific heat, meaning hydrogen bonds, can themselves store a lot of heat before they are broken. How would polar molecules interact with non-polar molecules, such as, let's say, methane? And how do we even know that something like that is considered non-polar? Well, if we look at our chart again, if if the electronegativity difference between two atoms is between 0 to 0.2, we would consider that nonpolar covalent. These numbers are not always definite, but they apply to most cases. So if we were to draw out methane, that's a carbon, and in its outermost shell we have we have 4 electrons. Then we have all these hydrogens that also have an electron to give. So unlike ionic bonds, these electrons are being shared, not given, and there's no charge that attracts the molecules together. But carbon does have a higher electronegativity than hydrogen. But let's look at the numbers and see if that's enough for them to be polar. The electronegativity of carbon is about 2.5. The electronegativity of hydrogen is 2.2. If we look at the difference, that's only about 0.3. Now let's look back on the chart, however. This chart clearly indicates that if it's from 0.3 to 1.4, it's polar covalent. But if we were to look at how methane reacts with water in a solution, you would say otherwise. Because if methane was polar, if it was polar, that means that carbon would be negative, the hydrogens would be slightly positive, and methane would be able to easily dissolve with water, right? But in experimentation, water and methane do not necessarily dissolve together, which is what allows us to cancel out the fact that it's polar. So we would have to assume that methane, CH4, is non-polar. So like I mentioned before, non-polar does not dissolve in polar substances. However, they do dissolve within their own. With the way that these non-polar molecules dissolve each other is by London dispersion forces or by van der Waals interactions. Those you do not necessarily need to know for biology, but it's a good idea to be able to understand why nonpolar dissolves nonpolar. A lot of times teachers do not necessarily explain that. They just say, oh, polar dissolves polar, nonpolar dissolves nonpolar, instead of actually explaining why that would occur. If methane is nonpolar, that means that we can generally assume that most of the hydrocarbons are also nonpolar. This means that a phospholipid, let's say, or at least a fatty acid and glycerol of a phospholipid, will be nonpolar. Now, how would this react in a water solution? Let's say we have a polar end. Let's draw out a phospholipid. This area has no charge, and this area does have poles because that's a phosphate group, and phosphate groups are highly polarized. And then we would look at water. It has a negative and 2 positives. So water has a slight charge to it. This means that the water would come here, and if we were to have many phospholipids in the solution, the other phospholipids would also be attracted, or at least the heads would be attracted to the water, while the tails would be attracted to each other. This is what allows the creation of the phospholipid bilayer membrane that you see in cells. What is pH? In pure mathematical terms, pH is equal to the negative logarithm of the hydrogen, or the amount of hydrogen ions in a solution. So whatever number of hydrogen ions you put into a solution, this equation will pop out a number as the pH. So let's look at a pH scale and what exactly it means. The scale goes from 1 to 14. 1 to 7 being acidic and 7 to 14 being basic. Some common acids are citric acid and coffee, while a common base is bleach. At 7 or around 7, depending on the kind of water it is water, H2O. Why is water at a pH 7 though? Well, let's see what happens when water is in a solution of itself. Because of the fact that water is polar, that means that it'll constantly dissociate itself, much like water makes table salt dissociate. So when water dissociates, it dissociates into H plus and OH minus. So as shown in the equation, the pH is the negative logarithm of the hydrogen ions. But an acid, by definition, is something that can release hydrogen ions, while a base is something that can release hydroxide ions. If water can do both, that means that it's both an acid and a base, which means that it's neither acid or base, because these two, the hydrogen ions and the hydroxide ions cancel each other out, thus making the pH of water 7. Why is pH so important to AP biology though? That is because there are buffer systems throughout your body and throughout nature that occur. And these buffers, in order to understand these buffer systems, you need to have a fundamental knowledge of how pH works, how hydrogen ions work, and how dissociation of ions also work. So these buffer systems are compounds, or these buffers are compounds that keep the pH constant. Instead of like moving the pH, like the goal of a buffer is not to make the pH of a solution 7. It's not to make it water. The goal of a buffer is to make the pH stay constant. For example, if I have my stomach acid at pH 3 and I want to keep it there, I don't want the food that I'm eating to affect it. Like if you're eating a lot of basic foods, you don't want it to affect it. If you don't want it, if you don't want basic foods to be able to affect your pH, you have buffers that constantly release hydrogen ions in that case, so you can keep the pH low. If they constantly release hydrogen ions, that neutralizes all those hydroxide ions coming from the bases that you eat, thus keeping the stomach acidity at 3. But why do we need to keep pHs constant though? Can't we just let it change and just let digestion happen or let other reactions just happen? Well, not always, because proteins that perform reactions need to be at a certain pH. Because if, let's say we have a protein, let's just put some scribbles and call that a protein. Say that outside of this protein there are too many hydroxide ions. And this protein is meant to be, or it's um over thousands of years, it's evolved to be, or the gene has evolved to create a protein that can only work when there's a lot of H plus. So if there's too many OH minus or hydroxide ions around the protein, that'll make the protein misfold and do weird things. So if the protein misfolds, that means that it cannot perform its function, as we will discuss in the biochemistry video. But enzymes and structural proteins will not be able to work the exact same and will not be able to necessarily fit their substrate if they don't have the necessary environment that they require. Hey guys, thanks for watching. If there's any part of the video that you missed, there are links on this screen. Make sure to like and comment on this video and be sure to also subscribe to this channel.